So last class, we just defined metric spaces. We will see more examples in this class. So before that, we constructed real line. I mean, for us, the construction of real numbers are just Cauchy sequence in rationals. Okay? So it is just a collection of Cauchy sequence in rational up to some equivalence. Okay? But then, for practical purpose, you can just consider any real number to be some number, natural number, times some, I mean, this is 1 up to 9, n1, n2, something like that, some infinite decimal expansion, something random. Okay? So this you can call it as real number. And if you want, you can truncate it at the nth place, nth decimal, and then consider that as that's a rational number, of course. And that as the approximation for this number. Or given any rational number, I mean, I don't want to write all these things. Given any, I mean, for example, a real number, which is actually a Cauchy sequence of rational number, you take in that sequence, you truncate it at the nth place. Or if you have some Cauchy sequence, some Qn or something, then you, I mean, then you truncate it at the nth place and take it up to, I mean, what do you say is, you have a rational number and you approximate it till the nth place kind of thing. Okay, then you will get something like this. You will be able to get something like this. So this is just justified. That's what I'm saying. Okay, so for our practical purpose, we can use this. Okay, so using that, we considered Rn, Cn with different metrics, and generally we had if we have a norm, if we have a vector space, we can define something called a norm, and through that norm we get a metric. Okay? So here is another example. S be any set, okay? Then you consider B of S. That is all function from S to C or R. Okay? Well, as I said before starting the lecture, I will do everything systematically. If you have already done, if you have already seen, or if it is trivial, then we will not do it in detail. But I want to record everything here. Okay. So this B of S is all bounded function, such that F is bounded. F is bounded, which is equivalent to saying F of P mod F of P is less than or equal to M, and this M depends on F. I mean, this is not true for all F or something. This depends on M. Or you can equivalently say that supremum of T in S mod F of T is less than infinity. Okay? I hope all of you know the definition of supremum. Supremum, if some, I mean, maybe I just say quickly, supremum of A over some set is equal to M. This is A is contained in real number, of course. Okay? This means that for every element here is less than M, number one. And if you take any epsilon, then there exists something in A such that which is greater than M minus epsilon. Okay? This is the definition of supremum. Supremum of some set A, this is the set here. Supremum F of T where T in S equal to, that's less than infinity. Say C or R, okay? Either C or R. Depends on whichever the vector space you want to consider. There is no quotient. Okay? You want to consider complex vector space or real vector space. Okay? So the definition of supremum is subsupremum equal to M. If every element here is less than M, that is number one condition. Second element is if you slightly below M by epsilon, there should be some element which should be greater than that in that set. Okay, that's the definition of supremum. Okay? So once we have this, then you can define norm F infinity to be just the supremum. Okay. And this is a vector space. You can see that this is a vector space. Everything follows from triangle inequality. And this is a norm. This is a norm. If norm F infinity, I will go quickly. I mean, I think it's okay. I mean, norm F infinity equals 0. That means these are all positive numbers. Supremum is equal to 0. That means F of T equal to 0 for all T. That implies F is 0, identically equal to 0. Okay. So the first condition is satisfied. And of course, 0 function has norm 0. And the second condition, if you have an alpha, you can take it as mod alpha. That's also clear. Okay. And the third condition is just third condition. You have to be a little bit careful. So you have F of T plus G of T is less than or equal to mod F of T plus G of T. Okay. which is less than or equal to, of course, I mean, this is the supremum. So norm f infinity plus norm g infinity. Okay. Now there is no t here. This is just a number. This is less than or equal to this for all t. Okay. This is less than or equal to for all t. So this implies norm of f plus g infinity is less than or equal to norm f infinity norm g infinity. This is how you should prove. First, you should prove this. Then you can take. I mean, something is less than some fixed number for all t. Then the supremum is also less than that. Okay. I hope you can verify that. That can also be verified using the definition of supremum. If not, then the difference there won't be anything between the difference. If this is not the I mean, you can actually from the definition you can go through that. And I think you should, if you haven't done it, you should do once in your life all these things. Okay. I mean, just check that if something is less than this and the supremum is also less than that, you should write a proof of that. Okay. If anybody has a trouble with that, you ask me to do here. Okay. I hope it's all you have done it in analysis one. So because of that, triangle inequality is satisfied. So this thing implies that B of S with this norm or D infinity, where D infinity of F and G equal to norm F minus G. Okay, this is a metric space. Okay? Metric space. Okay. So our L infinity, whatever we define, is just B of n. Okay. We defined L infinity, which is just B of n. The set is n. We defined all bounded sequences and defined the supremum norm in the last class. So which is basically this. Okay. And if you have S is any metric space, let X be any metric space. Okay. Metric space. Then I haven't defined continuity. So, okay, I will define it later. You know, I'm sure you know continuity. You can consider all bounded function, continuous bounded function that will be contained in that. But since we have already done real number, at least I will do this. C01, continuous functions, all functions from this we will consider. Okay, from to C or R. Okay. So all continuous function, f is continuous. Okay. This is contained in B01. Okay. Then you can restrict this metric on this. So this will be a metric space. Okay. The reason I am considering this inclusion is when we define closedness, this will be closed inside this. Okay. So when we want to prove complete, it's enough to prove this is complete. Once we prove this is complete, later I am sure you know the definition of completeness. Okay. Once we want to prove this is complete, it's enough to prove this is complete and prove that this is contained, this is closed inside that. Okay. That's enough to prove that. Okay. So this is, so we can consider this as a metric space. Okay. Or we can consider C1, which is all those f from 0, 1 to, you can consider C or R, doesn't matter, such that f is differentiable and f prime is in C01. Okay. Differentiable and the derivative is continuous. Okay. So you can restrict this metric here. That's one way. Then this is contained in this. That's one way. Or you can define a new metric on that, new norm on this, okay, which is f1 infinity, which is equal to f infinity plus f prime infinity. This is also a norm. Okay. If this is equal to 0, then both of them, they are positive. Both of them has to be 0. So that implies f is 0. And if you have an alpha, you can take it out. Triangle inequality will be, I mean, clearly satisfied. So this is also a norm. This will give you a metric. This is a different metric. Norm, I put a 1 on the top. Okay. I mean, just, or you can put it like this if you want. Okay. Doesn't matter. F1 infinity, which is f infinity from f prime infinity. Okay. And this is another metric. The reason I am considering this metric is with respect to this metric, this will be complete. Okay. With respect to that metric, that uniform metric, only if you have this, it will not be complete. Okay, so that will come to that. Okay, that's why we are considering different metric on this. Similarly, if you can consider CK01, which is just f from, I mean, which are fk differentiable. Okay. Then you can consider norm fk infinity equal to summation. So you can call this a 0 if you want, f infinity plus Fi. Okay, is ith derivative. This is just ith derivative when I put Fi or something. So summation I equal to 1 to k. Okay, it's just the uniform norm of the ith derivative. With respect to that, you can make this complete. Okay, or if you have C infinity, you cannot sum it infinitely. So if you have C infinity, which is all those function, I mean f from 0, 1 to C 0, 1. Huh? 0, 1, f is infinitely differentiable, like polynomial or power series or e power x and all those things, infinitely differentiable. Okay. Here you cannot do this sum because the sum may be infinite. So what we can do is the following: d of fg, we can define it to be norm of f minus g infinity plus, or you can just take f comma g, yeah, comma g equal to norm of f minus g k infinity plus 1 plus norm of f minus g k infinity. Okay, summation 1 by 2 power k. Okay. This will be less than 1. Sorry, this will be fk. One second. It will be just fk. This is just kth derivative. This is kth derivative. This is kth derivative. This is kth derivative. I take the kth derivative. Distance between f and g is fk. This is kth derivative. Fk minus gk. Then 1 plus fk minus gk. And I take the infinite norm of that. There is no k here. Only infinite. Okay. Is okay. F infinity is just the supremum there. There is no infinity comma infinity. No, it's just k up to infinitely differentiable means for any k it's differentiable. There is no infinitely differentiable. There is no this one. This will be a complete metric. But I mean, this will not be a norm. You cannot get a norm out of it. You only get a metric out of it. Huh? Exact. No, parallelogram is for inner product. It has nothing to do with norm. Many norms will not satisfy parallelogram. Norm has to satisfy the other condition. The alpha has to come out, all that. Okay. This is only a metric. It's not, it doesn't come from a norm. Say it again. I think the scalar one. I mean the scalar something like that. Okay. This will not come from a norm. Okay. What? Yeah, then that's also not a norm, no? That will not be a norm. Okay. You take g equal to 0, that will not be a norm. That is just the distance between f and 0. Okay. So under the norm fk, yeah, under the norm, yeah, norm k infinity, whatever, supremum norm, these things are complete. Okay. This one, this is just norm f infinity. Then take the ith derivative, take the infinite norm of that, sum up to I equal to 1 to k. It's just the generalization of this. Here it is 1. Okay. Norm f infinity plus norm f prime infinity. So you take k derivatives and sum all those things. Sum those infinite norms. That's all. Okay. That will give you a metric. Sum I equal to 1 to k. Yeah, that's just to show you there are many different metrics. Okay, that's all. Okay. So as you can see, that thing we have made it. This is less than 1. Okay, and then we have summed it 1 by 2k, and this is something. So that idea we can imitate to if you have a metric space, xd is a metric. This k equal to 0 to infinity. 0 is the just the f, yeah, 0 to infinity. Okay. Otherwise, it will not follow. Yeah. I mean, otherwise, if you have a constant function, it will be 0, right? So 1 by 2 power k, 1 by 2 power k. That is just to make it summable. K equal to 0 to infinity, then k is inside 1 by 2 power. Here, here, here I have already here, no? So that's why I have written bound to k. So if we have a metric space, okay, then you can define a new metric on this, which is bounded. A metric need not be bounded. Okay, I mean, it will not take the value infinity, but it can be unbounded. Okay, dxy can be unbounded. So if you have, you can define a new metric d of e0 xy equal to, I mean, I haven't verified that that's a metric. So, but the verification will follow from this, which is d of xy plus 1 plus d of xy. This will be a new metric. If you have a metric space xd, then d0 is also a metric space. xd0 is also a metric space. The reason for considering this is this metric is bounded. This is less than 1. This will give the same open sets and other things. The convergence, I mean, you can check the convergence in one metric will be equivalent to the convergence in the other metric, but this will give a bounded metric. Okay. To shall I show this as a metric? I mean, this will follow from this. Yeah, you have already done t by 1 plus t, which is an increasing function from all those things. So it's very easy. Only triangle inequality, you have to verify something, but you have already done. Okay, you can do this. Okay, so this is fine. So another example is you can take C01. Okay, on this you can define a new norm f1 equal to integral 0 to 1 mod f of t dt. Okay. This is a norm on this. So what are the things to verify? We need to verify something. The first condition is this is the only thing verified. I mean, it's clearly if you have an alpha here, the alpha will come here. You will have a mod alpha here. This will come out as mod alpha. Okay. So this condition is satisfied. Norm of alpha f is equal to mod alpha times norm f is satisfied. And the triangle inequality is also satisfied. That's clear. Okay. Triangle inequality satisfied because integral is monotone. If you have f less than g, then integral f is less than integral g. And you have triangle inequality for each t. So from that it follows triangle inequality. So I don't have to prove it. So, but I have to prove that if norm f1 equals 0, then I have to prove that f is 0. Of course, if it is a 0 function, then it is 0. The norm is 0. So I have to prove the other way. This is the only thing I have to prove. Norm f1 equal to 0, then I have to prove f is 0. But I have to use the fact that it is continuous. Okay, otherwise it will not be true. Okay. So norm f1 equal to 0. Suppose f of t naught is greater than 0. Suppose f of t naught is greater than 0. Okay. Then the function is continuous. Okay. So you can take, I mean, f of t naught is greater than 0. So around an interval around t naught, it's strictly greater than 0. Okay. So that's what you have to use the, yeah. So you take epsilon to be f of t naught by 2. Okay. I mean, I'm assuming that it's positive because I'm going to apply for this only. Okay. Assuming norm f1 equal to 0, suppose, I mean, assume without loss of generality, assume f is positive. Okay, because I'm only going to apply for the mod. Okay, so we can assume that. So there exists a delta such that t minus t naught minus delta on t naught minus delta t naught plus delta f of, I mean, this is on this f of t minus f of t naught is less than this f of t naught by 2, right? So that will imply f of I mean, f of t is less than, what is it? F of t is greater than f of t naught by 2 and f of t is less than, I mean, there exists a delta such that on this, the difference is less than that epsilon. Okay. So this implies f of t is less than f of 3 f of t naught by 2, okay, greater than f of t naught by 2. Okay. So if you take the integral, this is strictly greater than f of t naught by 2 in this interval. So integral mod f of t 0 to 1 dt is greater than or equal to integral in this interval t naught minus delta, no, delta t naught plus delta, okay, and f of t naught by 2, okay, which is strictly greater than 0. I mean, you have to, this is a constant, okay, so this is strictly greater than 0. Is okay, no? So which is a contradiction? I mean, we are assuming that this is equal to 0, which is a contradiction. Okay, is fine. You can use anything to come. I mean, this is those things. What did I show here? I showed the first property of the norm. Norm f1 equal to 0 will imply f equal to 0. That's the property of the norm. Property of the metric also. dfg equals 0, then f equal to g. Okay. The metric comes from norm. I want to prove that this is a metric space. Okay. That is C of 0, 1. This is a normed space or this is a metric space. It is a normed linear space. NLS means normed linear space. Linear space, vector space, normed linear space. So it gives rise to a metric. So the first condition of the metric we just verified. Other conditions are trivial. Okay. So similarly, another example is on C01. You can define an inner product to be 0, 1, f g bar f of t g bar t dt. Of course, if it is complex number, otherwise you don't need a bar. Okay. And this is clearly an inner product. Okay, is an inner product. And this gives rise to a norm. And with respect to that norm, you get a metric on this. Okay. So this is, I put a 2 here. Norm 2 equal to f square root of this. Okay. Then this is a normed linear space. Okay. C01 norm 2 is a normed linear space. I am assuming you know Cauchy-Schwarz inequality and all that. Using that, this is a normed linear space. Okay. This is another example. Okay. So on C01, you have already 3 norms. One is norm 1, norm infinity, norm 2. Okay. Okay. Repeat the which norm? 3 norms. Norm infinity, supremum norm, norm 1, norm 2. Okay. You'll see its properties later. Okay. Okay. So on the other hand, if you take all Riemann integrable function, I hope you can see this is integrable. I have written Riemann integrable functions. Okay. If you take all Riemann integrable function, okay, on this you can again define for f here, you can define norm f1 to be integral 0 to 1 norm f of t dt. Okay. This will satisfy the triangle inequality and you can take that, but it will give what is called a pseudo norm or a pseudo metric, because norm f1 equals 0 need not imply f of t equals 0 for all t. Okay. For Riemann integral, you can have finitely many places. You can have a step function or something which is 0 except some finite places. So it need not be a 0 function. So what it gives is what is called a pseudo metric. Pseudo norm or pseudo metric. This no one norm. All I am saying is if you call that R01 with norm 1 is a pseudo norm. Yeah, pseudo spelling correct. Pseudo norm. Without? Yeah, without. Yeah. And if you have just Riemann integrable function, it's a pseudo norm. It is just now, I mean, it satisfies triangle inequality and whatever that alpha can be taken out. It is just alpha taken out as mod alpha. It is only that, I mean, it is just the first condition is not satisfied. The positivity, strictly positivity condition is not satisfied. Okay. So it depends. If it is real, you just take it real. It is just C01. I consider it either a complex space or a real space. If it is complex, you use complex function. If it is real, I mean, I don't want to write separately both of them. Okay. If it is complex, you use the bar. Otherwise, don't use the bar. Any? You can do that. You can do that. Yeah. Any P, but I have to prove something more. Use some Minkowski inequality and all that, and you just have norm f power p similar to this. This two norm, how is defined? Now integral mod f square root of square root. Instead, you have p and square root of p. That will be the p norm. But proving it, we need to work. Okay? We need some Holder Minkowski inequality and all we need. Okay. So this is just a pseudo norm, but any pseudo norm, any metric space with a pseudo norm can be converted into a metric space by quotienting. Okay. We can define f is equivalent to g if d of whatever norm of f minus g. I mean, if you have any pseudo norm, you can do this. So maybe I will do it for any pseudo norm. We have done this. Okay, I will go there. Huh? I come up with the homeomorphic to the continuous functions. No, there is no need. But like in that case, like not the difference has to be zero. The norm of the means like the space of discontinuity must be measured zero, right? Could be. Riemann integrable, yeah, if it is, but still, it's not clear to me that it will give all continuous function. Yeah, you can, you can, there will be a continuous function in that, correct. You can change it in a measure zeros space and you will get a continuous function, yeah, I think so, yeah. I will write it again, I'll write. I mean, this is an example, okay. If you have a x d, okay, if d of xy, I mean, it satisfies all the other properties except that d of xy equal to 0 need not imply x equal to y. Okay, that's the pseudo norm. Pseudometric, sorry, pseudometric. I mean, if it is a norm, it's a pseudo norm. Okay, pseudometric. Okay, so if xd if d is a pseudometric, okay, d, I mean, we have xd and xd is a pseudometric. Metric. Then you can define x is equivalent to y if d of xy equals 0. Okay, and then you can define on the equivalence class. Okay, then you maybe you call it x tilde, okay. Then you define x is equal to x tilde to quotiented with, you take the equivalence class. On that you define equal to d of xy. Okay. Maybe you call this as d tilde, I call this as d tilde. Okay. X tilde, d tilde is a pseudometric. Then you define this equivalence relation. Then you define the new metric as this. Okay. And this will be a this is well defined. Okay. That is clear, because if you take something, use triangle inequality or something, and I think you have to verify well definedness, you have to use triangle inequality. If you take some other element is here, some other element here, okay, then the distance between that and x is 0, and the other element and y is 0. Use triangle inequality twice to get that this is equal to, that is equal to d tilde xy. Then the other things are follows immediately. Okay, so this will give you a metric. Okay, should I go through? Is it clear? Okay, so this implies XD is a metric space. Okay. Okay. So, okay, so we have recorded basic examples. Okay. I have already defined L1, all summable sequences, okay, which is a metric space and it has a norm. Yeah.
What are even integrable sum by the equivalence ratio? Find it out. Why do we not get the continuous sum?
And I didn't say you will get, I think. Yeah. We need a proof, but yeah. Okay. So this is summable sequences, okay, Xn, summation mod Xn is less than infinity, and take this as the norm, which I have already said, and L2 is all those Xn such that summation mod Xn squared is less than infinity, okay, and L infinity is all those bounded sequences, Xn bounded. Okay. Okay. And you define the supreme, in this we have already said this is L infinity of n, and the norm is precisely this. Okay, we have already defined. But here I missed one thing last time, so that's why I'm saying this L2 is a vector space. I didn't verify. You have to verify that L2 is a vector space. Okay, I mean this is a norm because it comes from an inner product. If you have two sequences Xn and Yn in L2, then you can define the inner product between them to be summation Xn Yn bar. This will give an inner product. From that you will get a norm, and all those things are fine. Except that we have to verify that this is a vector space. That is, sum of two Xn and Y1 is here. For that you have to use some, what do you use? You want to verify that Xn plus Yn whole square. Xn is in L2, Yn is in L2, then Xn plus Yn is also in L2. For that this is equal to Xn plus Yn into Xn plus Yn bar. Okay. And this is equal to norm Xn mod Xn squared mod Yn square plus 2 times real part will come, but that is anyway less than or equal to 2 times norm Xn mod Yn, right? I mean, I just swallowed it because I'm sure you are familiar with that. You will get a 2 times real part of Xn Yn, which is less than this. Okay. Now this is Xn square plus Yn square. Now this 2 Xn Yn is less than again Xn square plus Yn square. This whole thing is, where shall I write? This whole thing is less than or equal to 2 times mod Xn square plus Yn square. Okay. Because of that, this Xn plus Yn, this is also summable. This is summable, this is summable, so this is summable. So Xn is in L2, Yn is in L2, then Xn plus Yn is also L2. You need to go through this. Did I go fast or didn't I say clear? It's clear? Eh? Okay. So we are considering 3 vector spaces. One is L1, one is L infinity. L1, I will just say, okay, I'm finding it difficult to write. Okay. L1 is all those sequences such that summation Xn is less than infinity. And this is the norm. Norm of this sequence is equal to this. Okay. And there is no problem. If Xn is there, Yn is there, the sum is also there, and you can define the norm. Similarly, L infinity, this is bounded, and you take the supremum over n, that will give you a norm. Okay, that's also clear, very similar to what we have done already. Here, you have some Xn, and you can take the summation, all those square summable sequences. This you can, for here, you have to verify this is a vector space. Okay, to verify this is a vector space, if you have 2 sequences Xn and Yn in L2, the sum is also there. Of course, scalar times is clear. Sum is there, you have to verify. To verify that, if you take this Xn plus Yn square, mod Xn plus Yn square, which you can expand it like this, okay, which is less than or equal to 2 times mod Xn square plus Yn square. If you expand Xn plus Yn square, I hope you can see from there, which is mod Xn square, mod Yn square, then you will get 2 times real part of Xn Yn, which is equal to this. Which is less than or equal to this. Okay. And this is just geometric mean less than or equal to arithmetic mean, right? That's what this. Or you can take square Xn plus Yn square is, okay, it's basic inequality, which you must have seen from 8th standard. Okay. So it is basically that. And from that you get 2 times mod xn square plus mod yn square. Okay. So because of this, sum is also in this. This is a vector space. Once you have a vector space, you can define this to be the inner product on this. This inner product will give you a norm, and that will give you a metric. Okay. So that is the metric on L2. Hope it's clear, right? Okay. Yeah. Yeah, these are all sequences. Which converges? This converges. This inner product. So that's one another thing. What? Here. No, this is inner product. There is no root 2. He is asking. That's a good question. How do you know that this converges? Okay. So this converges because of, we assume that we have already proved Cauchy-Schwarz inequality. We have already proved, to show that this is inner product, we need to show that. Okay. We have already proved Cauchy-Schwarz inequality. You take finite sum, n equal to 1 to n, xn, this is a good question because we have to be careful about that, xn, yn bar. Okay. We know that mod of this, okay, mod of this, if you want, okay, is less than or equal to summation mod xn square root times summation mod yn square. This is just finite dimensional. Okay. Sorry, n, capital N. Or I just take the square of this. Okay. I think this is okay. I don't have the square root here. Summation n equal to 1 to n. Okay. Right. Now these are all positive, so I can take n going to infinity. Okay. Right. So this is just summation n equal to 1 to infinity. 1 to infinity norm xn square times summation n equal to 1 to infinity norm yn square. Okay. I mean, for finite, I'm applying the Cauchy-Schwarz. You have to use the Cauchy-Schwarz for finite dimension. Then I'm having this, then I can take the n equal to infinity. So this will be there. Now there is no n here. This is true for all n. Take n equal to n going to infinity. Okay. This okay, no? Yeah. Is fine. So I mean, we have to one has to show like this only. Yeah. Good question. Any other question? Yn square, yeah. Yeah. Okay. Okay. So this I will go there. Okay, I think we have seen enough examples. So I hope you know what is open set and all that. Quickly, without writing, shall I just say a few things? You know what an open ball is. If you have a metric space XD, open ball B of x naught R is of course all those y such that D of x naught y is less than R, right? Okay, this is an open ball. Okay, and yeah, if you have any set A inside X, you say something is an interior point. If you take, if some X is the interior point, if around that point you can draw a open ball which is completely contained in that. That's an interior point. Okay. So then interior of A is all the collection of all interior points is what is called interior of A. If interior of A equal to A, then we call it an open set. Okay. That means a set is A is open. For any point in A, there is an open ball around that which is completely contained in that. That's called open. Okay. So open is clear. Then we can define what is called a topology for any set. This I will just write it. If you have definition, X is any set means set we are dealing with. I mean, not any complicated set satisfying axiom of sets. Okay. Then you have some U alpha, a collection, some alpha in I is a collection of subsets. That is, this is contained in the power set of X. Okay. X is any set, you take the power set. This is just a collection, sub collection of the power set. Okay, U alpha is a topology on X. Okay, if the first condition X and empty set are in this collection, you call this as U. Okay, is in U. I mean, this collection is called U, script U. Okay. Second condition, if some U I, I in I, is contained in U, okay, then union of I in I, Ui, is also in U. Okay. You have a collection of subsets of X. Okay, it's called a topology. If the whole set is there, empty set is there, number one. And if you have a sub collection, then its union is also there. Any arbitrary union is there. Okay. And third condition is, if you have U1 up to Un is in this, a finite collection, then the integral I equal to 1 to n Ui is also in U. Okay. So you have a collection of subsets, okay, which is closed under arbitrary union and finite intersection is what is called a topology. Okay. So now I make a statement. I hope all of you, it will be clear. This is okay, no?
Can be uncountably misuse, but
Uncountably, yeah. Uncountably arbitrary union. It's closed under arbitrary union, finite intersection. Yeah. You want to ask something? Which norm? L2, yeah. Linear, what is linear? Inner product. Inner product is linear. If you have an alpha, you can take it out. Alpha, xn. Split what? Say it again. Ah, right.
but to define it now, in split it, you'll have to do rearrangement.
If you have xn plus yn, xn plus zn, okay, you will have xn plus zn there. Xn yn plus zn yn. That is a sum. What? Yeah, yeah, but it's absolutely summable, no?
Where is some? Not this.
No, no, the product is summable. Square is summable if the product xn yn is summable. They are all summable, absolutely summable. Xn, summation xn square is finite. You prove this first. Summation yn square is finite. Then summation xn yn, you take the mod. This is finite. Okay? Number one. Once you have this, you can do anything. It's good to have such doubts. This is okay. This is true, then this is true, which we have just noticed. Okay. Once this is true, you can do all those things you want. What's the problem? No, it's absolutely summable. Okay. This product, I mean, x and y, and that product is absolutely summable. Okay. Fine. Think over it. If you still have a problem, you will see. Okay. This one. No, this is uncountable. Any union. Any arbitrary union is there. Closed under arbitrary union. Finite intersection. Arbitrary union, finite intersection, and uncountable. What is asymmetry? Because the collection of open sets will not satisfy this. It is just that is the way it is. That is the way where it is. Yeah. Motivation is you have a metric space, you take the collection of open sets. Their arbitrary union of open set is open. Finite intersection of open set is open. Empty set is open, whole set is open. So it is just that. But you need, see, the point is a topology need not come from a metric space. This can be more general. That is a subject called topology, which you will study possibly in the next semester. Okay. So here we have the collection of all open sets, which gives a topology. That's all. Okay. So that's what I'm going to write. I hope you know the proof, so I'm not going to prove it, but I can say it orally if you want. I mean, quickly. Proposition is XD a metric space, okay. Then you have this, all those U contained in X, U is open, okay. You take the collection of all open sets, okay. Then U is a topology on X. Okay. The whole big set is, which is the universal set, which is open, because any ball you take, it's going to be there. Empty set, vacuously open, okay, and it's closed under arbitrary union. So suppose if we have an arbitrary union of U alpha, and if you have a X, it has to be in one of those U alpha I. There you have some open set which is completely contained in that, and that will be there in the union. So arbitrary union is true. For intersection, if you have a X, then it will be in all of them. This is only finitely many. So you have a X or Ri contained in Ui. Take the minimum of that. That will be that Ux. That will be in all the open sets. So the intersection is there. Okay, I said it orally. Since you have already seen, I am not writing it. Okay, we will spend more time on other things. So it's clear. Okay. So okay, but anyway, this is easy. So even if you have done something for compactness, other thing, we will go through the proof again. Okay. For these things, we will not go through. Okay. So this is about open. So this gives a topology. Now examples of open sets. Open ball itself open set, and you can take arbitrary union, or you can take any region in R2, just remove the boundary, that will be open set, and all those things. There are many things like that. For example, in C, whenever you define a set with a strict inequality, that will be open. Whenever you have a greater than or equal to, that will be closed. We will come to closed. Okay, this is a general intuition. Okay, in C, you have F naught, G naught in C01. Okay, then this set, all those H such that H of t is less than or equal to, sorry, not equal to, F naught t greater than or equal to G naught t, okay, for all t, this set will be open. I will not go through this. You just look. This is an example of an open set. This, all those H such that H satisfying this in C01 is open. Okay, exercise. You have to use continuity. Okay, all H such that H of t is greater than G naught t, less than F naught t. Okay. G naught and F naught are fixed. Okay. If it is greater than or equal to, it will be closed. Okay. You can show that. Okay.
And if it is like fixed on one side, then
Yeah, exactly. Something like that. Yeah. I mean, it's just an exercise. I don't want to give it as an assignment. It's not very difficult. Okay. Okay. Closed. I want to define closed. Okay. A sequence xn converges to x, okay, in a metric space if dx and x goes to 0, and you know epsilon definition and all that. These are all just positive numbers, so this goes to 0. Okay, this is fine. And if you have a set A contained in X, okay, and X in A is a limit point, X in not in A, X in X is a limit. I mean, it can be outside the set also. Is a limit point of A if there exists a sequence in A such that xn converges to x. Okay, this is definition 1. There is no f1 only. This is definition. Huh? What? Yeah. For all t. Open set. Prove it. Exercise. I didn't prove it, no, so I leave it as an exercise. Okay. So this is also I will go through quickly, so that I will do something non-trivial today. Okay. I think I haven't done anything non-trivial. Okay. xn, so this is the definition of limit. Okay, you can prove that. I mean, expected, I mean, the obvious way of defining the limit. And if you have any set, then a point in X is a limit point of this. If there X is a sequence completely contained in this, such that Xn converges to X, that's called a limit point. Okay. Then the third definition is A closure, the closure of A equal to all limit points of A. Okay. You collect all limit points of A. Okay, this is A closure. Then I write it as remark. A is contained in A closure because you have a constant sequence which will converge to that. So A is contained in A closure. Take constant sequence. Okay. So A is contained in A closure. That is clear. Number one. Number two, and another definition. I forgot to write another definition. Okay. Another definition. A is closed. Is that A is closed if A equal to A closure. Okay. If A equal to all set of all limit points. Okay. Then
What if I have like an isolated point?
the constant sequence will be there. You are confusing with this what is called accumulation point. I mean, when you in some book, for example, in Rudin, I believe, for limit point you exclude that point. I am not excluding that point. Okay, I mean that I would like to call it as accumulation point, just for the sake of two different definitions. Okay, because when we deal with something else like isolated point, we want to define what is an isolated point. For that, we need those definitions. Okay, you want a sequence which is not that point, but I can take constant sequence. That's what I'm saying. A is contained in closure. Take constant sequence. Okay, that will work. Okay. Okay. I thought you were going to ask something. Okay. A is closed if A equal to A closure. Okay. This is our definition. Okay. Then the second remark is A closure is closed. Is that very trivial? A closure is closed means what? We need to prove this. Okay. So, I mean, A closure is closed. This is what I'm proving. Okay. So, 2. Maybe I'll answer. Why is it true? So, what do you have to prove? If you, I mean, A closure is closed means what? A closure is equal to A closure. That's what you have to prove. That is, we have to prove that all the limit points of A closure is A closure itself. So, if we have a sequence, so suppose Xn is a sequence contained in A closure, okay, then the limit is also in A closure. That's what we have to prove. Okay. So and Xn converges to X and Xn converges to X. We have to prove that X is also in A closure. That's what we have to prove. So Xn's are in A closure. So there exists a sequence in A which converges to Xn. Some sequence Y, K, N or something converges to that. But we can take something very close to Xn. Right? Because Xn is in A closure. That means there is a sequence in A which converges to Xn. That means we can take some Yn which is very close to Xn. Okay, choose Yn such that d of Xn Yn is less than 1 by n, which is possible, and Yn is in A. Okay, now this Yn will converge to X also. Now Yn is in A. Now d of Yn X is less than or equal to d of Yn Xn plus d of Xn X, triangle inequality, which will go to 0. Okay, so Yn will go to X and X is also in A closure. Okay, so this implies A closure is closed. Okay. Okay. Because if it is trivial, you tell me. Okay. Then the next one is A closure is the smallest closed set containing A. Okay, that is clear. That is clear, I believe. You just argue it out. A closure is the smallest A closure. It's smallest closed set containing A. And interior of A is the largest open set contained in A. Okay. And also this thing, you should prove this. This is an exercise. Okay. You take, okay, I will first prove this. A is, I mean, prove this once. I will orally prove this. Okay. I will just say the proof. A is closed is equivalent to saying A complement is open. This, I hope you have seen this. A is closed, you want to prove A complement is open. So assume A is closed. A complement, if it is not open, then for some X, there is no open ball which is completely contained in that. So every open ball will intersect with that. Choose something from there. For each K, you choose, I mean, there is a Xk such that each 1 by K will intersect with A. Choose something from that, that will converge to this, but then this is not there, so it will contradict the fact that A is closed. So similarly, the other way, it's clear, more or less the same argument. If A complement is open, then you take any sequence here, that has to, the limit has to be there. If it is not there, then the limit will not have an open ball which is completely contained in that, so it's not open. So it's clear. Okay? So this is something very trivial. So, I mean, I should go slowly if it is the first course. Since you already know, I'm not going through that. Okay. So if anybody wants me to go through it slowly, I will do that. Okay. It will take some more time. Okay. So this is clear to you. Then what? So then this is an exercise. I mean, you should verify. This is easy, but you should verify these things. Should you write it as an assignment? A is any set, then A closure equal to interior of A complement. Okay. Right? Is that right? Is it correct? Yeah. Okay. So prove this. Use the definition and then prove it. Okay. Okay. I'm wondering. It's clear, no? You don't need it as an assignment. Okay. Okay, let's not do that. But it's better you do, I mean, if it is not very clear, not just by looking at diagram. So you have to write, I mean, by looking at a diagram, by drawing it, it will be clear. But you have to write the definition, proper definition and prove this. You should, it's better you do that, okay? In this kind of things, you should do it. And you will not do it after this year, okay? So it's better you do it. Okay. So we have done this. This is enough, I think. Now we will, yeah, I have time, okay. Okay. Now I give some new definition. So XD is a metric space. Then A is some set contained in X, and X is some element of X. Then you define dXA, distance of X from the set A, to be the infimum of all those A in A, D of AX. Okay, smallest distance as you will expect. Okay? The distance from some point to a set is the smallest distance, okay, where it meets. Okay, that's the infimum. Okay? Infimum of smallest, it may not be attained, so we call it the infimum. Okay, so this is how the distance between a point and a set. Okay, okay. Now proposition. This is very easy. dXA equals 0 if and only if X is in A closure. Proof. dXA equals 0. That means that infimum is 0. Please write those things. Okay, I don't want to write each and every line. Okay, I'm finding it difficult for me. Okay, so if dXA equal to 0, maybe from next week onwards, I will write each and every step. Okay? Maybe week after next week. Okay, so dXA equal to 0. That means that infimum is 0. That infimum is 0 means there exists. So if dXA equals 0, there exists a sequence AN contained in A such that d AN X goes to 0, right? Right? Infimum of that is 0 means that this is equal to 0. This means AN converges to X. Okay? This implies X is in A closure. Similarly, X is in A closure, you will have a sequence something converges, so it's fine. Okay? So it's fine. So the other way is also clear. So this is okay. Okay. Now with these things, yeah, I'll go there. Yeah, I have 15 more minutes. We'll do the following. Okay, this I will go through completely in detail. So this is a definition. XD is a metric space. Okay. And script A, all subsets of this, A is closed and bounded. Bounded means you have a big open ball where this is contained in that. That's what bounded. You know what is a bounded set. Okay? You have a big open ball which is contained where this set is contained in that. Okay? That's what is bounded. Here you define DAB. I mean, this is all collection of all closed and bounded subsets of X, okay, on a metric space. There you define AB equal to infimum all those epsilon greater than 0, such that for that I have to define something. If you have a contained in X, then you define A epsilon B A epsilon to be all those X in X, such that D of XA is less than epsilon. Okay. If you have a set A, this is just something like this, an epsilon difference. Okay. A set which is a epsilon neighborhood of a set. Okay. This is the neighborhood, epsilon neighborhood of a set. Instead of a point, I am taking an epsilon. Okay. So here infimum of epsilon greater than 0, such that A is contained in B of, see, this B is different, this B is different. Okay. Maybe this is open ball. This is different B. Okay. B epsilon, and B is contained in B of A epsilon. Okay. Subset, yeah. Sorry. Now that's what I wanted to write. I wanted to write subset. Yeah. Okay. Mathcal A to, there is no math. Mathcal A is the collection of all sets, and A and B are in that. This is a metric on that collection. You have a metric space, you take the collection of all closed and bounded sets, you are defining a function. We want to prove it's a metric. Okay. So distance between A and B is all those, take all those epsilon such that A is contained in the epsilon neighborhood of B, B is contained in the epsilon neighborhood of A, take the infimum of those epsilon. Okay. And that is the metric we are defining. We want to prove it's a metric. Okay. Proposition D is a metric. Metric on A. This is what is called Hausdorff metric. No mathematician. Expert of what?
And let D A B, you can write the supremum of A part of A, supremum of
A part of A means what?
small a,
Ah.
and of all B of DX AB.
DAB. You are saying it is just a DAB where A is in A, B in B. What is infimum? Oh, yeah, I think so. Yeah, anyway, I'll think about it. Okay. Okay, proof. So DAA is clearly equal to 0 since A is contained in B of A epsilon for all epsilon. Okay. A is contained, so the infimum is 0. Okay. A is contained in B open ball around A epsilon. So DAA is 0. Okay. Suppose DAB equals 0, that means for all epsilon greater than 0, A is contained in, that's right, no, this A is, or there exists, I mean, see, this for epsilon 1 is less than epsilon 2, A epsilon 1 is contained in A epsilon 2, right? So you can say this. I mean, infimum is 0 means there is a sequence which goes to this, but because of this property, you can say this. For all epsilon greater than 0, A is contained in B epsilon, B of B epsilon, and B is contained in B of A epsilon, for all epsilon. Okay. But then that will imply that, I mean, you have a that implies that A is contained in B closure, right? Right? You have a sequence here which converts to that, right? A is contained here means there is something with a distance from something from B, which is, I mean, at a distance. Okay. For all epsilon, this is true. Maybe take 1 by k, choose some B, and so, but B is closed. So this implies you can remove that since B is closed. So A is contained in B and B is contained in A. I mean, this implies A is contained in B. This implies B is contained in A because they are closed. Okay. A, B closure equal to B. We have to prove only triangle inequality. Okay. Let me see. Okay, we want to prove A, B, C are two sets. A is in B closure, A is in B. B is, we are taking only closed set, no? We are taking all A is closed and bounded sets. The metric is defined on that. I'm wondering whether that will be true for compact set or general closed set. I have to think about it, what you said. Yeah, for compact set it is clear, but for general closed set, do you know whether it is, have you worked it out? You read it somewhere, okay. It looks to me it's for compact set, but maybe for closed set it may not be true, I'm not sure. Okay, now you take ABC are in A, okay? Then you want to prove the triangle inequality, okay? So we want to consider these things. I mean, D of, we want to prove, D of AB, right, less than or equal to D of AC plus D of CB, right? That's what we want to prove. Okay. Okay. Let me call that D of AC some number, some X. X is okay. X, mu, and D of CB equal to some mu. Okay. Okay. Now this is equal to mu. This implies A is contained in the open ball with mu plus some epsilon. Right? Given epsilon, I mean, what I want to say is given epsilon, let me write it, given epsilon greater than 0, okay, let me write that, whatever I wrote. There exists a C, I mean, I want to use this condition, okay, D of AC equal to mu. That means this mu is the infimum of all those things such that A is contained in C, epsilon neighborhood of C, C is contained in epsilon neighborhood of A. Epsilon greater, epsilon greater than 0, I am going to take mu plus epsilon. So given epsilon greater than 0 and A in A, okay, there exists a C in C, such that d of AC is less than mu plus epsilon. Make sense? Correct? Just the definition. This is equal to mu means this. This is equal to mu. Use the definition. That means A is in the neighborhood of mu plus epsilon neighborhood of C. That's what I'm using. That means there exists a C in here such that d of AC is less than mu plus epsilon. Okay. Similarly, for this C, there exists a, what is this, B in B such that d of CB is less than or equal to nu plus epsilon. Okay. Let me take epsilon by 2 so that finally I'll get epsilon. You will be happy. Okay. Epsilon by 2. Epsilon by 2, epsilon by 2. Now this implies d of AB, that B, whatever the B we have got. A is any A. Okay. For any epsilon greater than 0 and A in A, we got this from the definition of mu and nu. Okay. But DAB is less than or equal to, of course, DAC plus DCB, triangle inequality, which is less than or equal to mu plus nu plus epsilon. This is true for all A. For all A, there exists a B. Okay. This implies for all A in A, I mean, for all may be misleading, for any arbitrary A in A, there exists a B in B such that this happens. Okay. From this statement, I am concluding this. Same metric. Where is 2 metric? Very good. Sure. Yeah, correct. I am using 2 metric. This is a small metric. I have to change it. There is a metric inside. So here itself the problem is there. What you created. So you have a metric here. If you want, you call it as capital D. Okay, then capital D is a metric.
Then the 2 metric, it will give the same distance, so it's fine.
This is fine. Let's take D. It's okay. Yeah. Let me change to capital D and small d. Okay, that's fine. Okay, so then capital D. This is all capital D. Okay. Yeah. I didn't have that in mind. Okay, so now we have this capital D. We want to prove this. Okay, right. Okay, so you call this as D, capital D. You can keep small d, and if you are not confused, it's okay. Okay, now there exists something. This is small d. Okay, now what I am saying is there exists some. These are all small d. Such that this happens just by definition of mu and nu. This is true. Okay, this implies this is true for all A. I mean, for any arbitrary A, this is true. There exists a B like that. This implies A is contained in this B neighborhood of mu plus nu plus epsilon. Okay. By the same argument, interchange A and B. Okay. By same argument, I mean, there is nothing about AB. You just interchange A and B, right? Same argument. By same argument, B is contained in B of A mu plus nu plus epsilon. This implies D of AB is less than or equal to mu plus nu plus epsilon. Yeah. For all epsilon. Okay. This implies triangle inequality. Wait, this is what D of A, C, and that's what. That's triangle inequality. That's all. Any question? Shall I explain anything? We have to prove the triangle inequality. and we called this as mu, called this as nu, use the definition. Then we proved that this is less than mu plus epsilon. For all epsilon, then take epsilon going to 0, you get this. That's all. Okay, it's fine.